This call is now being recorded.
Some properties of electrons in atoms. Some properties you're already familiar with of electrons is that they have mass and they have a charge. -1 and a very, very tiny mass. I don't know what the number is. But we have what's called principal quantum numbers that describe the location of electrons in an atom. We want to know specific things about where electrons are. Chemistry is about electrons. It is not about atoms. The electrons are what is part of bonds, and that's what making and breaking is about. Making and moving around electrons. The third principal quantum number is this mouthful, the orbital angular momentum. And it's not as complicated as it sounds right there. Another way to describe the orbital angular momentum is the direction of the shape of the path. That actually does sound like a mouthful, but that phrase, the shape of the path, is what I used in another video to describe the S, P, and D orbitals. So the direction of the shape of the path. Let's look at the orbitals and talk about why I'm using this phrase, direction, right here. If an electron is in the s orbital, it has a generic shape of a path that looks like a sphere. And we need to be clear that it's a sphere because the best I can draw here is a circle. The nucleus is not drawn. It's up to you to imagine it in the center right there. If there are electrons inside of there, they're not drawn. We're only looking at this outer shell of the onion right here. Now, the direction. On top of this sphere, please imagine an X, Y, and Z coordinate plane. Using the right-hand rule, I think I got this correct. The positive Z is coming out of the board. A sphere is uniform in every single dimension, X, Y, and Z. So a sphere has no direction, so we only need one s orbital to describe every direction. The p orbitals, let's remind ourselves of the generic shape of the path of electrons that are in p orbitals. Think of these as balloons tied together at the ends, or dumbbells, and the nucleus is right there in the center. If there are any electrons inside or outside, we're only looking at this layer of the onion here. Now, the direction of this P is not uniform. This P that I have drawn right here, we could say is the PX, because it lies along the x-axis. We could draw a PY, a p orbital that goes along the y-axis. And finally, we could draw a PZ a p orbital that goes along the z-axis. Now, I have individually drawn these p orbitals, but your mind needs to take these three orbitals and try to overlay them on top of each other. Because in the center, wrong color, because this is where the nucleus is located in these three p orbitals. And these p orbitals have a direction to them, but they have identical shapes, the shapes of the path. So there are 2 electrons that can fit inside an orbital. No more than 2 electrons. So in the S, 2 electrons is all that can fit in there. In the PX, 2 electrons. In the PY, 2 electrons. How many can fit in the P3? I'll give you a second to guess. You got it? These 3 p orbitals, I'm going to attempt to draw these overlaid on here. I hope I don't mess it up too much. I'm going to draw the PY. Then I'm going to draw the PX. Then I'm going to draw the PZ. It's really hard to kind of fit in the PZ right there. Because that's covering stuff, I'm going to erase some of the axes. I wish I just kept it. Okay. But those 3 p orbitals now overlaid on each other. Now let me show you a secret in the periodic table. The first principal quantum number, 1, 2, 3, 4, there's a blank periodic table where each box represents an electron. I know it looks like each box represents an atom, but that's a dirty lie. Each box represents an electron. The first principal quantum number talks about the distance, the average distance an electron is from the nucleus, whether it's closer or getting further away. The column tells you about the shape of the path. If the electron is in one of these first 2 columns, it has a spherical path around the nucleus. If it is in a p column, it has this dumbbell shape, whether it's px, py, or pz. I want to note something about how many boxes there are. We said that there are 2 electrons max that can fit inside of an orbital. We determined there was 1 s orbital that covered all of the directions. Look at how many columns this is wide. Just dose. There needs to be 3 p orbitals to cover each direction of the x, y, and the z. 2 plus 2 plus 2 is 6 electrons. Look at how many columns wide the p block is on the periodic table for each of the 6 electrons. We need 1 orbital to fit 2. We need 3 orbitals to fit 6. In Gen Chem, we don't talk about the Ds too much. We don't draw them. We don't use them in bond, and they're very much used for organometallic chemistry or metallic chemistry. But there are 10 d blocks here. There are 5 d orbitals. Thank you.